So our next speaker is Associate Professor Sun Ching Fhong. Dr. Sun obtained her bachelor's and master's degree in electrical engineering from UTM in 2011. She was awarded PhD in molecular and biomedical engineering from the University of Bradford, United Kingdom. Currently, she is the head of microelectronics and nanotechnology from the MINT-SRC Research Center, which is a center of excellence of UTHM. Her significant achievement is winning the Woman Bio-Innovator in Malaysia Science Innovation in year 2013. Let us all welcome Professor Sun.
Morning, ladies and gentlemen. Thank you very much for Primrose's very kind introduction. So first of all, I would like to thank Park System for this invitation. I'm really honored to be here. Right, so they have organized a very good platform, NanoScientific Symposium Asia, to bring all of us together to learn from each other about the scanning probe microscopy. Right, so my name is Sun. I'm from the Universiti Hussein on Malaysia. So I'm here to share with you about AFM for structural analysis of biological samples and also physical solids. Right, so welcome to all of you. This symposium. Right, so a bit of introduction on our university. So we are located in Parit Raja, Johor, which is about 2 hours drive from Singapore. So we have another campus in Pago and also in Tanjung Labo. We have about 18,000 students. So this is a bird's eye view of the university. And also this is where I'm working, at the Microelectronics and Nanotechnology Samsudin Research Center, SRC. So this center with a purpose of serving the researcher and also industry for sample testing. So today I'm actually talking about representing the center to share with you about our experience of AFM application in imaging different types of samples. So these are our services provided with small charges. So the AFM system that we have is actually quite an old system, XD100. However, we have fully optimized and utilized this machine for imaging many different types of sample, which is really interesting to us. Right, so I think Dr. Chu just now already introduced about the background of AFM. Right, so I'm just a small mission for all. So that is the nature of a lecturer who likes to give a small bit of a lecture. Right, then we'll focus on the main topic here, which is on the different types of physical solids or thin film that you can apply using, obtain their images using AFM and also biological samples. Okay, just bear with me. So maybe some of the information was shared, but some are not. So these are the inventors of the STM, Scanning Tunneling Microscopy, and the Binek and Roeder was awarded the Nobel Prize for the STM. So STM works on the quantum tunneling electrons, which is slightly different from the AFM. So AFM is a modification of the STM, right? So the STM actually works on laser light and also cantilever, whereas that is a probe and a sample. So they have a slight difference. All right, so you can actually refer to the publication in Physical Review Letters to know more about the first AFM images in 1986. So this is the first atomic resolution image of the silicon with a rotation of 111. Right, so it's really a magnificent image at the time. All right, so you see in 1986, already AFM can provide you very impressive images of the surface topography of CD, different waveguide and also polymer growth. I think now if you look at the latest series of the Park system, AFM is even more sophisticated and give you more functionalities. Right, so these are the general application of AFM. So mostly are for the thin film coatings, for different types of materials, ceramic, composite, polymers. You can even apply it for biological samples. So it actually comprises of wide applications. So you can actually study different mechanical process that are involved. Then you can actually get a lot of information through the AFM. Right, AFM also can be used for nanolithography or making structures in nano size, or you can even use it for nanoindentation to obtain the stiffness and hardness based on the force displacement curve obtained from the AFM. So it has wide capabilities. So we always look at the brochures. They show you fancy images obtained from, fancy images of materials obtained by AFM. So how true is that? So I will share with you what we have done in the lab. It's very similar. So we have actually looked into the application of AFM in materials and also in life sciences sample. Right. So here's a very simple structure of the AFM system. Basically, you put your sample on an XY scanner, then you actually scan your Z scanner over the sample. The displacement between the tip and the sample is collected by the laser diode irradiated on the cantilever, right? So when there's a changes of height between the tip and sample, that will be detected by the position sensitive photodiode. That's how we reconstruct line by line and form into a 2D AFM images. Right, so that is the tip and the atomic structure or sample surface. So we actually measure the force, repulsive and attractive forces between the tip and the sample. That will give you the reconstruction of the topography. Okay, so it's actually more than that. It involves a very high speed feedback loop system to continuously monitor the scan rate, also the tip surface distance. So it has to be very high speed so that your scan, what I call the cantilever, will not actually collide on the sample, but it will actually adjust to the topography of the sample. All right, so it has FM is just not limited to surface topography. However, today my talk is limited to topography, but it has wide application in electrical, mechanical, chemical, magnetic, and thermal properties measurement. Right, so it provides you morphology information, surface roughness, and also the physical properties information for your analysis. Okay, so there are different types of FM tips that depends on your application. What type of resolution you want, or is it that you're working on the ultra resolution AFM, then you need a sharper tip, right? So you can choose the right tip for your application, right? So this is a data sheet taken from our lab. So whenever we purchase a box of the Park system AFM cantilever, it comes with what they call a data sheet. So every cantilever has its own what they call their own specification. They are labeled in 1, 2, 3, and 10. Let's say you have 10 tips, then you have 10 different what they call the characteristic for the every single cantilever. So the important information is the drive percentage, the resonance frequency, and also the Q factor. So every tip mostly has a tip radius of less than about 10 nanometer. So another important information is the force constant. Okay, I'll show you in a short while these information are important. Right, so usually the resonance frequency of the cantilever is ranging between 200 kilohertz to 400 kilohertz. So this is taken from our lab. So this is about 315 kilohertz resonance frequency for this tip. Right, so this is another example of about 250 kilohertz resonance frequency tip. All right, so why is it that every single cantilever has a resonance frequency different? Right, this is based on this equation, omega equals to 2 pi f naught k over m. K is the force constant, then you have the mass. So you need to know the mass. If you do not know, it's okay. You know the oscillation frequency and the force constant, then you can calculate the mass. Right, so it's important to read about the cantilever specification. Right. Okay, so we have 3 different types of mode. I think most of you know it. Surface contact, non-contact, and tapping mode. All right, so tip is subjected to abrasion or damage easily because you contact with the sample. So that's why we have the non-contact mode that move over, oscillate over the sample. Or if you have a sample that has strong electrostatic charges, then you're advised to use the tapping mode. Right. So I'll focus on non-contact mode that measure the van der Waals forces difference between the tip and the sample. Right. So it's a good, measurement mode because it is not contacting with the sample. However, it's not advisable to use with a sample liquid that will give you artifacts. We've tried before, right? So we try to challenge this AFM system to measure the system in fluid, but the buoyancy of the fluid will actually affect the measurement, right? Okay, so I skip this one. Right, so what we measure in the non-contact mode, when you're doing the test, you have to do a set point. So it depends on the skill of the operator, whether you can get the right set point or not. If not, then you don't get a good imaging. Right, so when this set point is set, your cantilever will scan over, let's say, a step height sample, then you actually maintain the set point between the sample height, so that the differences between the error signal detected, your set point has to be 8 nanometer, but any differences occur is the differences between the detected position and the set point. Then that error signal actually give you the topography on a single line scan. Okay, this is a very old software C acquisition program. All right, so I was talking about all the settings here. You can actually set the set point here, and so the PID control and the P gain, and also the scan size. So it's really highly dependent on the skill of the operator. But I think with the new system here, it's so much easier than the system before. All right, let's come to the highlight of this AFM application. So as a research center, we receive samples of broad spectrum from different customers, right? So when they have requirement, then we have to accommodate to it. So we have tried different types of samples. All right, so before we start a measurement, make sure that we have a standard reference material, right, to ensure the quality of our scanning. So we have a standard reference material that measure 1.33 micrometer and 1.6 micrometer width, right? These are the standard. So every week we'll do a scanning to make sure that it meets the specification of the data sheet. Okay. All right, so the first one, these are all obtained from our lab. So we have the PVDF microfiber. So FM is very good in getting the surface structure of an intertwining fiber. Your fiber is how messy, but in a big size. I think AFM is very good at giving you this structural information in terms of the dimension and also the height of the sample. Okay, so this is obtained from my colleague, Professor Nafariza. He was actually doing sputtering of monolayer of aluminum nitride thin film on the silicon wafer. So he looked at the argon flow rate effect to the sputtering of the aluminum nitride. So you can see that as the flow rate increase, then the grain size of the aluminum nitride sputter is getting smaller. So your FM actually, the FM actually give you the roughness information. It doesn't reflect in the FSAM, but it actually give you the FM give you the details of the roughness and also the grain size. Okay, so this is another one. I've got the permission from the main author that published in WHERE, which is a Q1 journal. So look at the effect of the annealing temperature to the different composite of metallic material. All right, so they're actually interested in what happened when the annealing temperature increased. Right, so this is another work done in our lab, which is doping the gadolinium into zinc oxide for the application of spintronics. Yeah, so as the doping percentage of gadolinium increase, so the grain size increase, and also the MFM, magnetic force microscopy, indicate that the force distribution is also around the grain size. So it depends on the grain size of the gadolinium doped into the zinc oxide. Right, so a maker of toothbrush asked us to, this is another industry that asks us to scan their toothbrush sample. All right, so for compact disc, they give you a repetitive structure, right? So you can get it. But how about something that has a CD that has been burned? Yeah, you have burned the data, you radiate a laser light on the repeating structures. This is what happened. So you can see all the data, indicating as peaks, all the peaks in the AFM images. Okay, so this is a hydrogel that has been dried for biomaterial application. So sodium alginate thin film that indicate the porous structure of that alginate, sodium alginate, right? A topography of a stainless steel. Yeah, so it's not that homogeneous actually in nanometer structure. So these are all very simple material to us because they are just thin film, nothing interesting. Right. Okay. This is something that is more challenging. All right. But we can do it in a simple way. Okay. Although theoretically it says, you put immobilize your sample, your fiber onto the polymer or nail polish, but you don't need to do that with the XC100 system. Just simply tape it onto a glass slide for your fiber. Then you can actually start scanning already. It shows how stable is the Park system in imaging microfibers. Right, so this is a carbon nanotube alginate under the AFM. So the fiber was produced using wet spinning technique. Right, so let's see how the carbon nanotube alginate looks like. So you can't see the carbon nanotube actually because you have encapsulated with the alginate. So it's all covering up. This is how it looks like. But we can show you the carbon nanotubes. This is how it looks. The carbon nanotubes are in the bigger particle. Okay. We also try to challenge the system, see whether it can scan particles or not. Right. So this is a MXene, a new material, titanium carbide. Right. So was prepared with hydrofluoric acid delamination. All right. And also this the carbon nanotube. Just simply cast it on a glass slide. All right. So carbon nanotube under FM not so good. Maybe because our tip, the tip radius is too large. Maybe. So we are not able to image the nanomaterial, but however, we are still able to see some structural changes here. All right, so this is the line profile of that carbon nanotube. Okay, this is the particles of the MXene. Right, MXene is a very new material because it's a new emerging material that has very good functions for RF filtering. So it's actually attracting the attention of the scientific community. Right, this is how the MXene looks like in multi-layer. So surprisingly, I didn't know that this AFM also able to scan the multi-layer structure of the, the titanium carbide. So it's kind of interesting, but we have tried in a few attempts because it depends on how good the particle is stabilized on the surface. But you see, we are able to determine the thickness of the MXene. Right, so this is something interesting to us, right? Okay, so then we look at if we can apply FM in polymeric material, polyacrylonitrile, pen fiber, right? So this is what we get. We see a lot of fibrous structure. And all these spikes are actually showing that it's not so well mixed in the DMF, right? So then you can actually use the software to look at the distribution size of this or this undissolved or pen, right, that is found. So you can see how good is your dissolubility of the pen in the DMF. All right, surface roughness. So this has a surface roughness of average about 6 nanometer. Okay, finish. So let's see some more challenging samples. So physical solids is quite boring sometimes to me. Right, so to do biological sample application with the AFM, so you need to do sample preparation. First, these cells are live cells, so they are wet. So you can't do very good imaging with the wet sample. You need to do fixation and also dehydration. So first you fix it with formaldehyde, then do a serial alcohol dehydration, get the dry sample, then you're able to image it. Right, so this is how the cell looks like, flattened on the glass substrate. Cells are like human. If you give them a hard substrate, they behave hard to you. So they are flattened and stick onto the surface. You can see all these are the lamellipodia and also, these are the filopodia and so the lamellipodia and the nucleus are here. All right, so this is actually one of the organelles in the cell. So comparatively in the FM also able to give you all the details of the filopodia in nanometer. Okay, very elongated like finger-like structure, right? So the thickness of the cell you can see from here is nanometer, whereas the FISM cannot give you. So this AFM already complemented the images obtained from the FISM, right? So how about application of biomaterials to study the interaction of cell and the biomaterials? We look at cell adhesion on the glass substrate, also cell adhesion on the liquid crystals. Right, so we found that if you've exposed a cell to different substrate on the glass and liquid crystals over a time frame, you can see that the cell actually move over the glass and spread. That's very common for cell biologists, nothing interesting. But if you put it on the liquid crystal, the cell remain rounded on the substrate because of the stiffness, the low stiffness of the liquid crystal of the glass substrate. Right, so that's interesting. I mean, application of AFM in imaging this. right? Right. If you put in the PSAM, then because of the liquid crystal, it will actually disturb the electron flow, right? So PSAM may not give you all the solution, especially we are dealing with some, what do you call that term? Amorphous material, sorry. Amorphous material, yeah. Okay, so we compare the cell spread area over time. You can see that the cell spread on the liquid crystal is very less significant different from the cell spread on the glass. All right, so these are the line profile of cell spread onto the liquid crystal and the glass. Okay. All right, that's it. So we found that FM is a very useful tool to image the topography of a surface, then for give you different properties of a surface and allow you to know the roughness, right? So non-contact mode AFM is very useful actually in imaging a broad spectrum of material, but we have to interpret very carefully, right, if there's any artifact, right? So thank you very much for your attention.
Okay, thank you very much, Dr. Sun. So any questions for Dr. Sun? So Dr. Sun, we have one online question. So what type of imaging mode do you use for cell imaging in liquid? I will repeat, what type of imaging mode do you use for cell imaging in liquid?
Right, so we have not successful doing AFM with the cell in liquid, right? As I said just now, because of the buoyancy of the water, it will actually affect the vibration of cantilever. You'll get artifacts instead of getting a proper structure. So what we have done is all in a dehydrated form, right?
Follow-up question. In liquid mode, which tip do you use?
In liquid mode?
In liquid mode, which tip do you use?
As I said again, so we have not actually tried on the liquid mode. I mean, we have tried, but it's not successful.
Okay.
Right. So
okay. Yeah. Maybe another question. What did you mean by the cell membrane thickness?
Cell membrane thickness is what we measure on the AFM from the surface of the glass to the highest point of the cell membrane. So how thick is the cell? All right. Yeah.
Okay. Okay, last question for our online. Can you give some more details of fixation of cell?
Fixation of cell, I think is quite a standard procedure. You can refer to our publication. Right. Fixation of cells, basically you apply formaldehyde to form the methylene bridges between the biopolymers of the actin filaments, then you can fix the cells.
Okay.
Right, thank you.
Yeah, any other questions from the floor, from our on-site participants? Okay, so if not, thank you very much, Dr. Sun.